Hi, and welcome to this lesson on receiving antennas. The first component in a receiver is an antenna. An antenna is used to capture power from a wave incident upon it. Now the question is, how much power is captured? Although there are many other questions we could ask about antennas, which are used to receive signals, this is really the key issue. In the vast majority of problems involving radio link engineering, involving radio astronomy, involving spectrum management, all we really need to know is how to get from that instant power density to the power delivered to the rest of the receiver. And that's what this lesson is about. The enabling concept is called effective aperture, so we'll start there. Next, I'll introduce the antenna theorem, which is an amazing and frankly counterintuitive idea, but also one which helps us to answer our question in a relatively easy way. We'll talk about the effective aperture of some simple antennas, namely dipoles, and also some relatively complicated antennas, namely reflector antennas and phased arrays. When the smoke clears, we'll be left with an amazingly simple result, namely that the effective aperture of any antenna, and subsequently its ability to capture power from an incident wave, is related in a very simple way to the directivity of an antenna. Now, directivity is a transmit concept, and this idea that transmit and receive performance are related in a simple way is often referred to as reciprocity. Let's get started. Okay, we're interested in the amount of power, P sub r, captured by the antenna. As a starting point, let's consider what the incident wave is providing to the antenna. That's easiest to characterize in terms of spatial power density. We're going to call the incident spatial power density capital S with superscript I. And remember that this has units of watts per meter squared. And the direction from which this power arrives is important. For sure, the antenna is going to be good at capturing power from some directions and relatively bad at capturing power from other directions. So we'll say S super I is a function of the angular coordinates theta and phi. We should also account for the fact that the antenna is going to capture more power if the instant electric field intensity is copolarized with the antenna. We'll do this by attaching the subscript CO to S super I. So, the incident wave is described as the copolarized spatial power density, S super I sub CO, incident from the direction theta phi. This wave arrives at the antenna, and in response, the antenna delivers power P sub r to whatever it is attached to, which is probably a receiver. So we want an expression for P sub r in terms of S super I sub CO. Now, one thing we can say about this expression is that the received power is going to be proportional to the incident power density, right? In other words, if we double the incident power density, then we expect the received power to double. This relationship suggests a constant of proportionality, and we can see right away that the units of this constant are going to be meters squared. Then watts per meter squared for the power density times meters squared for the antenna give us the desired units of watts for the received power. But we have one other thing that we should consider, and that's the transfer of power from the antenna to whatever it is, probably a receiver, that's accepting the power from the antenna. We don't really want to unnecessarily complicate the problem by considering this aspect of the problem now, so what we're going to do is redefine P sub r to be P sub r max, meaning the maximum power that the antenna could deliver to the receiver. The electrical engineers in the audience will know that this condition can be achieved when the receiver is conjugate matched to the self-impedance of the antenna. However, all we need to know now is that everything is set up for the maximum possible power transfer from the antenna to the receiver. So, just to summarize, remember that the equation that we are developing applies to the case where we have both a fully copolarized incident wave and perfect conjugate impedance matching with the receiver, so we have maximum power transfer. Now we can define our constant of proportionality. We'll call it effective aperture, and we give this the symbol A sub E. And we note that this has units of meters squared. We further note that the effective aperture depends on the direction from which the power arrived. So A sub E, the effective aperture, is a function of theta and phi. The formal definition of effective aperture then goes like this. Effective aperture is the ratio of power delivered by an antenna to the incident copolarized power density, assuming a conjugate matched receiver. So, now, the question is, how do we determine A sub E? Well, one method would be simply to perform the measurement that's implied by the equation on this slide. You could illuminate the antenna with a wave having known power density, then measure the resulting received power, and then divide received power by power density to get effective aperture. Do that over and over again for every direction theta phi. Alternatively, if the antenna is very simple and you're sufficiently clever, you could instead do the physics and get an expression for this, as opposed to doing the measurement. That's usually not practical except for very simple antennas. The third approach is that you could use some kind of electromagnetic simulation software to work this out. What I'm going to do in the next few slides is to show you what to expect for a few simple but important cases. Here's what we find for the simplest physically realizable antenna, namely the electrically short dipole. When we say this dipole is electrically short, what we mean is that the length of the dipole is much, much less than one wavelength. For example, dipoles which are 5% or maybe up to 10% of a wavelength in length can be considered to be electrically short. Here, the wave arrives from the direction theta, as shown in the figure currently on your screen. Note that theta is measured from the axis of the dipole to the direction of incidence of the wave. So, theta is 90 degrees for broadside incidence, and theta is 0 degrees if it arrives from along the axis of the dipole. Theta is obviously important to know here, since we expect the received power to depend on theta, and so we should expect that the effective aperture also depends on theta. We should not expect anything to depend on the other angular coordinate, phi, and this is because the dipole has perfect radial symmetry around its axis, that is, in the phi coordinate. In this case, the reference direction for the copolarized electric field intensity points as shown in the figure. That's the red arrow. Now, this is important. For example, if the electric field vector is rotated 90 degrees around the direction of propagation, then we have perfect cross-pole, no copole, and the antenna receives nothing. So, whatever we work out will be for an electric field vector which is perpendicular to the direction of incidence, but otherwise aligned as closely as possible with the axis of the dipole. And because this is the direction of the copolarized field, this is therefore the orientation that will maximize the received power. For the ESD, we find that the effective aperture, A sub E, as a function of theta and phi, is given by the expression now appearing at the bottom of your screen. A sub E is about 0.12 times wavelength squared, times sine squared theta. As we anticipated, A sub E depends only on theta and not on phi. Also, as you perhaps anticipated, A sub E is 0 for theta equals 0. That is, when the wave arrives from along the axis of the dipole. And also, A sub E is maximum when theta equals 90 degrees. That is, when the wave arrives from any direction broadside to the dipole. What might be surprising here is that A sub E does not depend on the length of the dipole. Let me say this another way. If the dipole is electrically short, then its effective aperture does not depend on its length. Now, this is pretty remarkable, and it's a pretty useful thing to know. Don't misunderstand this result. Dipoles are not always electrically short. For example, you could have dipoles which are, say, greater than 1/4 wavelength long, and you would totally expect to see the effective aperture of those dipoles does depend on length. The result shown here does not apply to those dipoles. It only applies to dipoles which are truly electrically short. Hey, there's one other thing you should know about this result. Even though effective aperture, A sub E, has units of area, effective aperture is not physical area. The physical area of this dipole is essentially 0, yet the effective aperture is very different from 0. Now, this will get more complicated later in this presentation, but for now, just know this. Effective aperture of antennas is not necessarily related to physical area. Now, we're ready to talk about the antenna theorem. The antenna theorem states that the effective aperture, averaged over all possible directions, equals wavelength squared divided by 4 pi. Now let me say that again. It turns out that if you take a sub e as a function of theta and phi, and you average this over a sphere surrounding the antenna, then the result depends only on wavelength, and not at all on size or any other details of the antenna. Also, remember wavelength is phase velocity divided by frequency. So yet another way to say this is that the average effective aperture of any antenna is inversely proportional to frequency and depends on nothing else. Now, this relationship is anything but intuitive, and you may wonder how we know this to be true. One way to think about this is that it is essentially a statement of conservation of power as we consider the transformation of power from the wave to the antenna terminals. A proper derivation of this result requires some additional physics, a bit of thermodynamics, and some non-trivial math. It's not really a difficult derivation, but it's outside the scope of what I want to accomplish in this lesson. If you're interested in this derivation, and I hope you are, one place where you can find it is in the textbook cited at the bottom of this page, and in a number of other decent textbooks. For our present purposes, it's sufficient merely to know this expression, what we call the antenna theorem, and to know that it applies to any antenna. Next, we'd like to consider something that will initially seem ridiculous, but once again, I ask for your patience. The ridiculous thing I'd like to consider is the effective aperture of an isotropic antenna. What I mean by isotropic in this case is that the antenna receives equally well from any direction, such that the received power depends only on the incident power density and not at all on which direction from which the power was received. In other words, we're defining an isotropic antenna to be one which has effective aperture which is constant with direction. Now, the reason this is ridiculous is because there is no physically realizable antenna which has this property. If you don't believe me, try this experiment. Take a dipole antenna and try to twist the wire in a way that makes its performance independent of direction. It can't be done. You may recall from a previous lesson that the notion of isotropic antenna turned out to be useful in the transmit case. That is, an antenna which transmits power density uniformly in all directions is also impossible. But it turns out that such an antenna is a useful benchmark against which to describe other physically realizable transmit antennas. And now we'd like to do a similar thing in the receive case. So, let's see where this goes. We have an antenna whose effective aperture is constant with direction. What is that constant value? Well, we can figure that out quite easily using the antenna theorem. For an isotropic antenna, the effective aperture in any direction is equal to its average effective aperture. And the antenna theorem says that this average effective aperture has to be wavelength squared divided by 4 pi. Now, 1 over 4 pi is about 0.08. So we find that the effective aperture of an isotropic antenna is about 0.08 times wavelength squared. Very roughly, the effective aperture of our mythical isotropic antenna is about 1/10 of 1 wavelength squared. Now here's why we go to the trouble to consider isotropic antennas. For an isotropic antenna, effective aperture is equal to average effective aperture, which is equal to wavelength squared over 4 pi. But in general, that is for any antenna, we find that the effective aperture is greater by a factor, and that factor is the directivity. Now, let me remind you that directivity emerged in a previous lesson when we considered the transmit properties of antennas. Specifically, the directivity of an antenna is the increase in power density radiated in a specified direction, theta phi, relative to the power density that would have been radiated by an isotropic antenna. Now, we're finding out that the directivity is also the increase in the effective aperture in a particular direction relative to the effective aperture of an isotropic antenna. In yet other words, if we know the directivity of the antenna, we also know its effective aperture. It's simply directivity times wavelength squared divided by 4 pi. Now, how do we know this relationship between effective aperture and directivity? This is a consequence of the presumed reciprocity of the antenna. Reciprocity is a bigger idea than I have time to explain in this lesson. You could take a look at that textbook reference I cited a few pages back for details. For our purposes, it suffices to know that as long as we satisfy the conditions required to assert reciprocity, which is nearly always the case in practical work, then the effective aperture will be equal to directivity times wavelength squared divided by 4 pi. Here's an example of how this works out for two important types of dipoles. We've already worked out that the maximum effective aperture of the electrically small dipole is about 0.12 times wavelength squared. Another common dipole is the half-wave dipole, which is not electrically short, but rather is 1/2 wavelength long. The maximum directivity of the half-wave dipole is 1.64, whereas the maximum directivity of the electrically short dipole is 1.5. To calculate the maximum effective aperture of the half-wave dipole, we need simply to multiply the maximum effective aperture of the electrically short dipole by the increase in the directivity. So 0.12 wavelengths squared times 1.64 for the half-wave dipole divided by 1.5 for the electrically short dipole gives us about 0.13 wavelengths squared. A modest but significant increase in effective aperture. On the left are the patterns of these two dipoles. Now, I showed these in a previous lesson on the directivity of the dipoles, but what we now know is that these same curves represent the effective aperture of these dipoles. That is, the transmit patterns and the receive patterns differ only by a constant. This is another consequence of reciprocity. So far, our examples have involved antennas with very low directivity, but some antennas have very high directivity. An important class of these antennas are aperture antennas. An aperture antenna is one which can reasonably be described as gathering power through an aperture. What I'm showing here is one representative of this class of antennas. This is a small reflector antenna for home satellite internet access. This antenna focuses whatever wave is incident upon it onto a feed, which is mounted in front of the reflector. So this antenna is capturing the incident power density through the process of optical focusing. In this case, it seems like the effective aperture should be directly proportional to the physical size of the reflector. And this is in fact the case. The math in this case is pretty simple. The effective aperture is proportional to the physical area of the reflector. Let's call that A phys. Phys for physical. The constant of proportionality, identified here as epsilon sub AP, is what we call aperture efficiency. Aperture efficiency is some number between 0 and 1, which says how much of the power that we scoop out of the wave can be delivered to the antenna terminals. So here you can think of the reflector as that scoop. Essentially, it's a window in space through which the wave would normally pass, but is now captured. And you can think of the aperture efficiency as a measure of how much of this captured power we are able to deliver to the antenna terminals. And of course, this is only the maximum effective aperture, since it depends on the wave arriving from the correct direction. If the wave instead arrives from some other direction, then our virtual window is oriented in the wrong direction and captures less power. Another type of aperture antenna is the phased array shown on the right. Now this happens to be a phased array for a military aircraft radar, but what I'm about to say applies to all kinds of phased arrays, including those used for commercial communications and even for radio astronomy. A phased array consists of an aperture which is filled with many low-gain antennas which individually receive power, and then that power is combined in a separate step in electronics. Now, these constituent antennas are all very close to each other, such that all the power that would ordinarily pass through the aperture is instead scooped up by the constituent antenna elements, and then subsequently combined in the electronics in that separate step. So, like the reflector antenna, we have essentially a scheme in which the power flowing through a virtual window in space is captured. And also like the reflector antenna, we can describe the maximum effective aperture as the product of the physical area of the aperture times an aperture efficiency. Now, you might wonder what values of aperture efficiency are possible for these kinds of antennas. Well, The answer to that is that the aperture efficiency in most practical, well-designed systems ranges from somewhere between maybe 50% to maybe as high as 90% in some cases. So, if the antenna can be described as an aperture antenna, as it can for these two types of antennas, then it's true that the effective aperture in the direction in which it is greatest will turn out to be a pretty good fraction of the physical area of the aperture. Okay, time for review. Effective aperture, A sub E, quantifies the conversion of incident power density into power delivered by an antenna. The definition assumes that the antenna is copolarized with the incident wave, and also that the antenna is conjugate matched to the receiver for maximum power. To the extent that either one of these conditions is not true, the received power will be less than that predicted by multiplying power density by effective aperture. For that matter, if you have loss within the antenna, that will further reduce the power that you receive. Also, note that we often talk about effective aperture as the maximum effective aperture. That is, if someone says that the effective aperture of an antenna is X, then they probably mean that the effective aperture is X in the direction in which the effective aperture is maximum. Of course, the effective aperture in other directions can be as small as 0, those directions corresponding to nulls in the pattern. We talked about the antenna theorem, which is simply the fact that if you average effective aperture over all directions, the result is wavelength squared divided by 4 pi, and this is true for any antenna. We came up with values for the maximum effective aperture of the mythical isotropic antenna, as well as for the realizable, electrically short, and half-wave dipoles. In all these cases, we find the effective aperture in the direction in which it is maximum is in the neighborhood of roughly 1/10 of 1 wavelength squared. This is a useful order of magnitude number to know. We also talked about the effective aperture of so-called aperture antennas, such as reflector antennas and phased arrays. For these antennas, we find the effective aperture is equal to the physical area of the aperture times the aperture efficiency, and that aperture efficiency is usually somewhere between 50 and 90%. Finally, the headline result from this lesson is really the equation shown at the bottom of this slide. We find the effective aperture is equal to directivity times wavelength squared divided by 4 pi. This means that if we know the transmit characteristics of the antenna, then we know the receive characteristics of the antenna, and that's a very handy thing to know. That concludes this lesson on receiving antennas. Thanks for listening.